Welcome everybody, I am Santiago and in this video I will show you how do we use Nullspace software at Johannes Gutenberg University in Mainz, Germany to develop ion traps. I will show you what we consider to be the most useful features, our workflow with them, and some exemplary results. So, first, let's start with some background to our group, Schmidt-Kahler AG group. In which we work mostly in the develop of we work mostly with trapped ions quantum computing, which which is thought to be one of the two main um, architectures for achieving usable and scalable quantum computing together with superconducting qubits. To do so, we need to develop the hardware. It's what's concerned to us now. You can see some in this picture some of our processors, quantum processor, let's say, and those processors consist on several electrodes, which are supposed to generate very precisely shaped potentials. That's why we need Nullspace software. So, why do we need it? Why is useful for us the Nullspace software? First, for us, we think it's very efficient and very reliable simulations are the most useful for us. We need to get the potentials due to each independent DC bias electrode, and then also the the potentials due to all the RF bias, radio frequency bias electrodes, because as I will show you later, those are very relevant in the functioning of the very fundamental physics behind trapped ions quantum computing. Well, we use it in two ways. We can do whether um, compare uh, already built traps, compare with measurements, with experimental measurements, compare them with the simulations to see whether everything is okay. For example, we have already discovered that we have some shorts in our electrodes by comparison with the simulation from Nullspace. But also we can use it to design uh, new potential new potential traps shapes, because we can, as I will show you now, we can really easily change the dimensions of the electrodes and get the potentials. So the heaviest part of the simulation is to obtain the electrostatic potential for each of them electrodes. Then we can easily post-process to get most specific results that we would like to have. So now let me switch to BNZ, where we work with Nullspace. Well, here we have with already open Nullspace prep, in where we do the the CAD design of the trap. Uh, I will go straight to how we use it. The most useful feature for us is this here. Uh, yes, this here, the Python console, in where you can directly um, write Python commands and execute them. And then here you can execute the native qubit commands, which generate the primitives of the model. But a very useful thing is that you can also import already written programs. I will go here. Yes, for example, this is one of our Python script. You can see all of these qubit point CMD are the actual qubit commands, which actually generate the geometry. But all of those variables could be easily changed uh, because it's in Python. So I will now we can whether copy the text, the code and paste it here, or we can play a journal file. If we select Python files, for example here, well, I made a mistake. I will show you then what happened because I forgot to display geometry. Now what the program is doing is generating all the well, I will start again. Yes, we reset, deletes everything, and we do it once again. Python files, yes, yes, you can see everything is done within seconds, and with the dimensions you define in your Python script that you can easily change. Now it's doing the mesh, and now it's generating the different blocks that for us will be the independent set of electrodes. So this is one of our future designs. We are now going towards designing, instead of the state-of-the-art linear three-dimensional ion traps, we are going towards designing 2D uh, 2D linear three-dimensional linear traps. That is, instead of having just one of these rows, each of them is a linear trap, we will have a lattice of linear traps, but they need to intersect between each other, and there is where the physics become complex. So we need to do very careful simulations. And Nullspace allows us for really address subtle variations in geometry. For example, well, I will stick with the geometry. You can see here, this is the most relevant part, and we can easily change this width, the height of the electrode, the separation of the electrodes. All of them could be easily changed by just varying one of the variables in the Python file and run it again. So first, once we have all the geometry generated, then we define the mesh. This is the mesh. Into each of those triangles, the electrostatic simulations would be solved in a linear, would be linearized. That's how, if I'm correct, that's how this software, the Nullspace software works. So once we have this mesh, as you can see, the mesh, this is since it's just a demonstration, we use a very coarse mesh. For our actual simulation we would make much smaller uh, mesh elements, but you can see that the elements are much bigger in the outermost parts of the electrodes with regards to the innermost. That's why the our ions would be in the center along the x and y axis. So the closest by electrode surface are the most relevant. So when we have the mesh, we have now to define, to tell the program what we want, how we want to define the different independent electrodes. And you can see here that all we have defined here, all these highlight electrodes would be RF bias electrodes. So then when we later go to Nullspace ES simulations, all of them would be computed at the same time because they are an electrode. But then we will have, for example, this is an independent electrode, a DC bias electrode. This is another, blah, 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 blah. And here we have pairs of electrodes because we expect them to be at the same bias. So after we have defined all these 39 different blocks, which are the independent electrode sets, we export the mesh file. That is, we export a file which defines the position of the vertex of all these triangles, so, all the mesh elements, and also it's assigned each of them to an independent block. Then we go to Nullspace ES for electrostatic simulation. So to run electrostatic simulations, to run Nullspace ES, it's done in the terminal in this case Linux. So you just run the command, and then you have to, let's see, wait, first let's go to our directory. So you have to first have to provide an input deck file that you can see here. This is the command to get the example, all the options you have. And that input deck define the mesh file here, well, the scale, a lot of other stuff that we don't really use now. We define the electrodes, which are we are going to excitate, because all of those here we can see all of these 39 electrodes, we are not required to simulate all of them each time. So we can, if you just want to get the potentials due to just these electrodes turned on and all the other electrodes grounded, we could have it. So uh, I will show you now the input file. This is what we have, but the actual usage we do of that is that we first solve for the surface charge distribution. We first solve the electrostatic equation to get the distribution of charge on the mesh elements, and then after that, in a separate simulation, we evaluate the potentials where we want in the 3D space. So, what does Nullspace ES do for solving? Well, what it does is for each of the blocks we have defined here, each of the electrodes, it solves the electrostatic equations for the case in which the selected block, the selected electrodes, is biased at 1 volt, whereas all the other electrodes are grounded. And this is done for each electrode. So first, if you say here, we say here that we want 1 blah 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 up to 28, let's say, the first simulation would be all the RF electrodes at 1 volt, all the surface at 1 volt, and all the other electrode surface at grounded. And then when we go to number 2, just this electrode will be at just 1 volt, and all the other will be grounded. So let's switch now. I will show you the workflow we do. We have here a Python script that's sum up all the outermost process. We first here define the post-processing function that they do not concern to us now, because they are in the they have nothing to do with Nullspace. We've defined some parameters. We define the grid file. Here we write the grid into the grid file, and what we do is pretty sure this could be done in a better way, but what we do is to have a template Python file in which the variables are not in which the variables are a value, and we export that template file. We replace the values, we overwrite the values of those variables, and we save the file again. And with that file is the one we run here. Well, here we can do that. We modify the script and save it, and then we use subprocess from Python to first run the Nullspace ES simulations without opening the graphic user interface. Just read the Python script, export the files, and close. Once that has already been done, we run the Nullspace ES simulation to get the charge distribution with the newly generated mesh file. Then we run Nullspace again, evaluating the newly computed charge distribution in the grid file we have stored here. And after that, we have the potentials. And then we post-process the potential. First, we have to retrieve the values from the database file. This is the database files in which the potentials results are stored after running this command. So yes, the post process is not relevant for us. I will show you now. And I forgot to say that here I was just performing a parameter sweep on the dimensions of the model. I was varying both the width of this electrode here, of those shape, the width and the extension. And then we have all those set of data, we can see with our post-processing function which could be better for us. That is the workflow, our actual workflow for potentially new designs for ion traps. Now I will go back to the PowerPoint. I will show you the other way to do it, which is to import the model uh, for real life ion traps already built to simulate and get very to the best extent as good as possible to get the potentials to account for its behavior of a trap. So, well, this is the SolidWorks CAD file that we use for 3D for laser etching. That's how we made these traps, the production process. And we import the same file. Maybe sometimes we have to adjust some dimension, but we import the same file, and then we defeature unnecessary geometry features, and we select the relevant surfaces. We can see that these here are all the RF electrode surfaces. All of this would be the block of RF electrodes, and this one here are the DC surfaces. In this case, all of this will be just one block, and in this case, we will have pairs of DC electrodes. So after that, we can see here that we mesh all the stuff, and we can see the exemplary results of our post-processing. This is the pseudo-potential energy due to the RF bias electrodes. The equation for this is what you can see here, where E is the electric field. So we have the square norm of the electric field. This is the drive frequency of the RF. This is the charge of the electron, and this is the mass of the ion. So the pseudo-potential energy is what the ion will actually feel, because since this frequency is so high, the ion actually sees the average on time. And those are the parameters we use to evaluate the function, because as I told you before, Nullspace ES, what it gives you is it's the base, I think called the unit potential, when the relevant electrode is biased at 1 volt and is the electrostatic potential. So the field here will include the amplitude of the amplitude, because the results of Nullspace ES are just biased at 1 volt, no 370 amplitude. So, but you can see that, for example, these results are very useful for us, because we can see that at least this is the x-axis, we could maybe we could trap already an ion in the center of the trap. that is one of the objectives of the junctions we are designing. So I will go now to the last slide. What you can see here is how we would like to be able to use Nullspace at the end. Well, I already show you this to the Python script file with some initial parameters I show you there. We would then can generate the mesh file with Nullspace prep, then generate compute the potential and evaluate compute the charge and evaluate the potential with both the Nullspace configuration files, the input deck file and the grid file. And then we start our post-processing. In our case, we use the multiple expansion to evaluate the Hessians. That's the Hessians is what the magnitudes most relevant to us because they determine the vibration of the ions, which are very relevant in trapped ion quantum computing. And then we are around here. Then we would like to be able to using these processes magnitudes, we would like to be able to compute transport ramps, that is the set of voltage biases as a function of time for each DC electrodes that's allow us for moving an ion through the junction. So we have to be able to move an ion from one linear trapping region to the another through the junction, and maybe curving at the junction, not just going straight past, but maybe to the left or to the right. And we have to be able to define some theories of merit. I don't know, the speed of transport, the heating, the motional heating the ion gets by doing so. And then we could use, eventually we are intending to use maybe some reinforced learning or some other machine learning tools that will allow us for learn from those first merits to learn something about the initial physical parameters, the dimensions, which were the initial parameters to the geometry and mesh Python file. One we have learned something from the theories of merit, we would change those initial parameters and run another iteration again. So thank you very much for your attention, and thank you Nullspace for the opportunity to show this. And well, see you next time.